I'm Austin Chu. I'm lead software mentor for Team 971. So this is a class about test-driven development. So this is going to be interactive, by the way, in case you didn't get the hint. Does anyone know what test-driven development is? No. Okay. Oh, one person.
Is it where you test the mechanism or your code in code before you put on an actual machine to not break anything?
That's part of it. It's slightly more than that. The idea is you write a test. We try and confirm that something works or doesn't work. And then we go write the code to make it work. So first your test should fail because your code doesn't do anything yet. And then we will go fix the code and write it, and then it should pass. So that's the basic idea. So for this, I have another class or workshop where we're going to model this. But assuming that we have the model, and if you come back tomorrow, we'll model this. We can write a quick little simulation for this. We can then use that to simulate our sensors, and then we can write code to program that, and we can write tests to confirm that it's behaving as we expect. So we're going to do that as a group. So I'm going to rely on you guys to help me figure out what to write. I've written this a bunch of times, but you guys should be part of this. So let's start. Okay, so let's walk through it. I have a skeleton here, so we don't have to start writing everything from scratch. Let's start with our header. So we have an elevator loop here. We start out. So this is our main function here. So it's the update function. We pass in an encoder value, whether or not the limit sensor is triggered. So this tells us if the elevator is all the way down to the bottom or not. And then a Boolean for enabled. And then we call this, and as the comment says, we're supposed to call this at 100 hertz, and then it returns back the voltage to be applied to the motor. So this gives us kind of an API so that we can go use this in a simulation, and we can also use this on a real robot. Does that make sense? Okay, so let's start. Close the CC. So we got pretty much a blank slate. Was it 20 minutes ago, 30 minutes ago? We just finished getting all the constants for this robot, the simulation here. So hopefully we got these right. And then here is our main equation. So this is the core equation for our simulation, which we worked out from the physics. So this says, given a voltage and a velocity, we can compute the acceleration. Okay. So from that, we can build up a little simulation. So let's start by, we'll write a quick function. What should this look like? Any guess? I should probably walk you through some of the math that we'll do tomorrow. So we're going to do, it's called Euler integration. It's really simple. Basic idea is given an acceleration, we can compute a change in velocity. So say we have some function of velocity or acceleration. Acceleration is a function of time. So the idea is to get from acceleration, sorry, how do I want to do this? So we have this equation, right? So for a constant acceleration and going for a bit of time, we can get a change in velocity. Okay. So we can use this with our graph here, that if we do this for a bunch of little slices, and we just add them all up, we can get a pretty decent representation of what our velocity will be as a function of acceleration, or as a function of time. Okay. So from that, and computers are fast, so we can actually make this time slice really small and not worry about it taking a bunch of time. And from that, we can go build up our simulation function. So let's start in. What do I have? It's a dt. Oh, we want time. So we want to cut it up into really little slices. So let's say we'll do 0.1 millisecond. So then how would we rewrite this? Anyone have an idea?
Same formula.
Okay. So what would that look like?
Where do you have your velocity? And your initial velocity?
Good question. Let's set it to 0. I forgot to initialize it.
Is equal to so velocity is equal to velocity initial plus acceleration times time.
Yep. Great. I think this gets us what we want there. So acceleration times time gives us velocity. And then we're going to do, so we're probably going to be giving it, so it's a 10 millisecond time slice for our control loop. And then we're going to do a 0.1 millisecond slice here on our graphs that we're a little more accurate. So I think if I coded that right, that'll give us that. So how would we get position? Because our elevator thinks about position.
Position is equal to velocity initial plus 1/2 acceleration time squared.
We can do that, or we can actually just do this again.
I would say
It's a computer, so we can just, it'll be close enough. So its position is velocity. Well, it's the same equation. So x1 equals x0 plus v times t. Forget that.
What is your DT like decrease?
Great. Yeah, we have a question. Thank you. So what I'm trying to do here is the time that we're using is this small time.
Mm-hmm.
And then I'm trying to run that until we've gone long enough.
Okay.
So I'm being a little loose here. So if we take this time slice out of dt every cycle through, it'll get smaller until we've had that much time elapsed. And then each time we go through, we're using that here. Okay. Cool. Okay, so then we should be able to actually use this with our elevator loop to actually do something. So what could we put here?
Can I see your method? Can I see the method?
Yeah. Up here in elevator loop.
Uh-huh.
So these are the important ones. So update's our main method.
Yeah.
So we should call that. So what's update going to give us?
I'm done with it.
it's going to give you the voltage.
That gives us the voltage. So now let's see what I call that variable. Elevator loop. Elevator. Great. Okay, we'll fill that in a moment. We need to go find an encoder, a limit sensor, and an enable bit. But until then we can go simulate, right? So we can call simulate time with our voltage here, and then here's our DT. Okay. So we just got to fill in. Our update method is asking for the current encoder position, and then if the limit switch is triggered. So how can we make one of those from our simulation? Oh, that was wrong.
Well, you have position from the simulate time.
Okay. So we just return the position. So,
Yeah.
okay. And then how can we simulate a limit switch?
Say yes or no.
But we can do it from our physics simulation.
You can say if position is past a certain point.
So physically, if this goes low enough, right?
Yeah.
It's off, on. So if it's below a point, it'll turn on.
Yeah. So, do you know what that constant is?
That's a great question. So let's see if I wrote notes down on what it should be. I left some candy constants. We're gonna say it's 0. Without loss of generality. That look great? Okay, so let's try using it. And then we're just going to say this one's enabled all the time. Okay, oh, one more thing. Should probably set a goal, right? What's a goal? We'll pick a number.
Well,
12 meters?
it's
Yeah.
in
It's like through the ceiling.
1 meter.
Okay. Should we try it? Test pass. Did we test anything?
No.
Okay, we should test something. It's a start. They at least run, so we did pretty good. So what would be something useful here to test?
The position at the end of it,
Okay.
if it's equal to 1. Or close to 1.
Inspect near. About how close? That seems good.
Plus or minus 0.1 meter.
So 5 centimeters?
Yeah, that's a lot.
That's a lot, okay.
Half a centimeter.
Let's try. And if we get this wrong, it's a test. We broke nothing. Ah, test failed. Okay, we made progress. Okay, so what do we have here? We have our failure. The difference between 1 and position is 1, which exceeds half centimeter, where 1 evaluates to 1 and position evaluates to 0.
So it didn't move.
It didn't move, which is good because we didn't program it yet. So here we have our, yeah, we got to do that next. But on the plus side, we wrote a test and it failed, and so now we have something to work on fixing. So, okay, so let's see if you can spot why this didn't do anything.
Because there's no reason in there.
Yeah.
Returns 0 all the time. So we should fix this. So I'm going to propose, let me draw up how I think how the software should look. We're going to flowchart it out a little bit, and then we can work on programming it. So I like to kind of treat things as cascading filters. So you have your input signal coming in, it goes through various steps, and then you get your result. So our request in is we get a goal. All right, that's for the box. So the basic idea is we need to zero this thing. So if this thing starts up in the air, which this one seems to like to coast down, so this may be less of an issue. But if it starts up in the air, we want to slowly move down until we hit the limit sensor. And then write that number down so we know that that's 0. And then we want to then be able to go to position. So this lets us take a goal. So say the user wants to go to 1 meter. We can then modify that so we can slowly move down to go to our starting point, or to go find the limit. And then we can use a little control loop to go do that slowly. Because we don't want to go too fast because we really don't want to break the robot. And again, on some of the other robots we've worked with, this one seems to settle pretty nicely. But, okay, so let's talk about, we should make this a little state machine. Do people know what a state machine is? Seeing some nods. So what would, no. I don't want to. Good question. how do I describe a state machine without drawing this one? Basic idea is you have, like say you have uninitialized and running, or two states, for example. And then you can define, say you do something when you're in the uninitialized state, like you don't move, and in the running you do something else, and then you can define transitions. We'll do a really simple one. So on enabled, this one's almost trivial enough it doesn't warrant being a state machine, but you start here in uninitialized, and then whenever the robot turns on, we transition to running, and then we can change our behavior, and then we can go back. So we can use this to go implement our zeroing behavior. So what might our states be for this? Uninitialized. Sure.
When it's not zero yet.
Okay.
I'm just gonna steal this. Keep drawing this.
What else?
0.
0. I'm going to call that running.
Disable.
Do we actually care? Not really. It's a good thought. The goal is to be as simple as we can be here, but without losing functionality. Okay, so let's see if we can capture the logic we want with this. So uninitialized, when would we, I'm going to relabel this to zeroing rather than unzeroed. So when would we want to transition from uninitialized to, I'm assuming we're going to start here. Robot turns on, it's disabled, we start uninitialized. Then we're going to want to transition from there to the active zeroing at what point?
When the robot is enabled and position is greater than 0.
We don't know where we are when we start.
You just enable.
Okay. We got to get to running somehow. How are we going to detect this? Okay. Okay. So what happens if we're in the active zeroing and the robot disables?
You go back a step to uninitialize.
Yep. We didn't succeed, so we might as well just try again. Rather than get clever in here, we can just reset it, start over. I think this might capture it. It's a pretty simple little state machine. So let's start programming it. Let's see what we get. I'm going to build the skeleton and then we'll fill it out. Okay, so what do we want to do in these different states? Somebody?
In 0, you want to slowly lower the elevator or quickly, depending on the type of
Okay.
that you have, until it hits the 0, until it hits the limit.
So how would we capture that? You're right. You're completely right. We just got to figure out how to code that right to break that down a little bit more for the machine.
You can just turn the, or an elevator gearbox, or spin the motors relatively slowly into the elevator.
Like to do it with our little loop here.
Just spin whatever you negative.
Again, we'd like to do this a little more controlled. So we'd like to go past a sequence of goals that slowly move down.
Or all your poles are moving, check it until you make your position.
Well, so while zeroing, we want to slowly move our goal down at, have a constant for this, k zeroing velocity. And then once we see the limit set switch, then we can just do the state transition. So we need to capture that somehow. Let's start with a filtered goal. And then in zeroing, we can do lower that. We're going to move every cycle through zeroing, we're going to move it down. Where's the equation? Velocity times time, that much position. So we'll just slowly keep shifting it down. Okay. We should get our state transitions coded up though. So right now it's going to get stuck in the, well, let me try it. Oh, that's cool. Now test still fails, so we have some work to do. So we should probably get our straight transitions encoded. So how would we write those? Slowly.
When it hits the limit switch to
Okay. That's that one. So then we need a couple more.
Are we assuming that as soon as we run the test, we want to enable?
Yes. Well, actually, we have an enabled tool, right?
So then you can do that in your initialize.
Okay. Okay. And then we should probably do the other side of that. If we're not enabled. Okay. So how are we going to start? How are we going to figure out where to start? I just set filtered goal to 0, which is going to not be great.
What is filtered goal?
Filtered goal should represent this. Our little state machine decides what goal to pass through.
Should be like gold minus 7.
Sorry, complete your thought.
Like gold minus some like small distance.
Oh, sorry. Does that get us the behavior we want? Okay.
Oh, do you have your current position? So then it should be your current position minus like that point on.
Well, it's going to come around next time to do it. So first time through the loop, it's going to set it to the current position. Next time through, we're going to be in zeroing. So we're just going to move it down a slice. So we're going to get the behavior you want. Okay? Should we see if it worked?
It won't work because we don't have that.
Yeah, well, didn't work because we're still returning 0.
Yeah.
So we should probably write a little PID loop there then. that give us, oh, I need a KP and KD. So we have our, I'm not going to do an interval controller because I don't think we need it. So we have proportional to our error and then proportional to the change in error. See if it moves this time. Oh, no. Oh,
Oh,
progress. So now it's stuck at 0.
How long is the test running for?
It's running for, that's a good question, 2 seconds,
Okay.
something. So I propose we figure out how to plot this. I think that'd be very helpful. So the easiest way to plot is going to be to write out a CSV file and plot it. So what should we plot? Right position. Position, velocity, voltage. Seem
Error.
decent? Okay. And then we'll need to. I guess we just print last error. That way. I'm gonna be bad. Write a getter since it's for debugging. One, two, three, four. All right, cool. Position's going slowly down. Let's plot some more things. Oh, it's title. Okay. We'll plot voltage. Okay. That's curious. Okay. I guess we can plot error. That's a proposal. mainly what I'm trying to show here is our debugging can be really simple. We're just printing out values and plotting them. This could be Excel rather than GNU plot, which is what I know how to use quickly. Just do debugging for this stuff. It doesn't have to be very complicated. But, so let's keep debugging. I actually think it'd be really useful to print out which state we're in.
Yes, sure.
So let's add that. One, two, three, 6. Oh, I need to save. Oh, we got to state 2. So that state 2 is going to be running. So it actually got to running, and then it didn't perform very well.
What did you 0?
Yeah. Well, and also look at running. What do we do with our goal? Not much. So what should we do here?
Use our PID.
Well, what do we want the goal to be?
No.
But more specifically, I believe we have a variable for that.
Oh, yeah.
So it's whatever the user asks for.
All right.
Should probably give them what they asked for once we zeroed. Oh. That's progress. It's getting there. Looks like we're just voltage. Oh, voltage is my error because P is 1. Okay. So it's trying to use 1 volt to move 1 meter. We read it here.
I think
Does that seem aggressive enough?
No.
Okay.
I don't know if that's really.
Because if we do the dimensional analysis here, we have volts here. Our error is in meters. So what's the units of kP? Volts per meter. So 1 volt per meter. Probably a little low. So let's see what 10 looks like. 10 better? Better. Our test got closer. We're at 4 centimeters there. But we can be more aggressive than that, right? Pick a number.
13.
We'll try it. Oh, we can go higher than that.
25. Oh, 30.
Actually, looks better. And our test passed, actually. We've actually done something getting closer to our goal.
And that was in 2 seconds.
Yep. So it's taking, we don't know when it exactly passed, but looking here, it's getting pretty close.
You can make the PID more aggressive.
Do a little more. Well, it's a simulation, so we can go way more aggressive. But I'm not sure. Well, that oscillated.
So what is that called? When it, I've seen that, like, if you go too far, it'll start to create like this sine wave or something.
So, So this is called critically damped. These are terms. Critically damped is the fastest you can go before you start oscillating. This is underdamped, so you're going to see some what's called ringing, which is it's ringing. And then this is what's called underdamped, which is what we had when we started. It was very, very lethargic.
Maybe it never gets there.
Yeah. In this case, it'll get there.
Because of simulation.
Yeah, because it's simulation. But in the real life, friction will sneak up on you and kill it. But, yeah. Control's a lot of fun. Okay, so obviously we don't want 500, and I don't think our robot would behave quite like our simulation if we were to use this game. Our simulation's pretty basic, it doesn't have friction, doesn't have backlash, all those things. So we should back this down. 50 didn't seem crazy. Just personally, I'm looking for in this plot, want to see this, it should converge in a quarter second or so. Should be quarter second, should be a decent number for this. If we go too much faster than that, it's going to start ringing and we're going to start to have problems with our hardware. Too much slower than that, and it'll take a long time. But this one actually looks like we might not need derivative, because that's pretty well behaved. So again, if you can get away with a simpler controller, that's great. So, okay, so we're getting somewhere. Plot it, and then I'll point out something. So where did we start this thing? What position?
Support user.
Okay. We want to support starting at non-zero positions. So we should probably test that. Because we did the easy case. So we should modify our simulation to go, oh, another thing here. How many volts is that?
13.
Do we have a 13-volt battery? Should we allow that?
Probably not.
Okay, so tester and development, what should we do first?
Right.
Great, so let's write a test that needs to fail. So where should we put that? Where would you guys recommend? Pick a spot.
Okay.
Oh,
Should we put it in simulate time? Should we put it in our for loop? What would you pick? Okay, we'll put it up here. I'm going to be a little sloppy with the syntax. We're going to say the voltage needs to be within 12 units of 0. Then I don't have to do compares. Okay, so then our test should fail. Yep. We asked for over 12 volts. So now let's go make a pass. How do we want to modify our code?
So when you return voltage, you just say if voltage over 12, return 12.
Oh, hold on. Oh, perfect. I pre-planned. So the basic idea, one of the concepts that we use on 971 is if you're not zeroed, I don't really want that thing using 12 volts. So we have a max voltage we can use when you're zeroed and a max voltage you can use when you're not zeroed. So okay. I will argue that will do that. Okay. Ah, good, test pass. We made progress. Okay, so we should do our test or we should modify our simulation now so that it doesn't start at 0. Okay. We said that wasn't real. So how do we, how do we want to do that? Any ideas?
Well, you have your position variable, so you could set it to.
Sorry, speak up.
Oh, you have your position variable, so you could set it to a non-zero number.
So what would that, let me ask you a leading question. So if I go to here and turn the robot on, what will the encoder be?
0.
Okay, but what is its position?
Not 0.
Not 0. So we need to make sure our simulation captures this. So I'm going to be slightly better. So good, we set the initial position. Then, how do we make our encoder work? So we can, for grins, we can make a test for this. Great. Encoder reads 0.2 and we start, which is wrong. So how do we want to fix this? Is it now?
Yeah. Thank you.
Was that your bag?
Oh, yeah.
We just subtract the initial position. Okay. So we still failed. Let's go check our plot. Oh, we're still, what state are we in? 1. So we're zeroing. So we're still going down. Did we wait long enough? No. It's still trying to 0. So we just need to make our test wait longer. Let's try that. Oh, cool. So we actually are seeing here, right, we're seeing that it finished zeroing, and then it went and did a motion. But where did it end up?
Above 1.
At 1.2, rather than 1. Which we can see here.
Oh, because everything's outside.
Yeah, because we don't have any logic here to capture what the encoder value was when we zeroed. So we should probably add that. So this is cool because we caught a bug that would have potentially destroyed our robot. We caught it in simulation. Let's try. Sorry, I'm going to rush slightly so we can end early. This normally is a 2-hour workshop, but there are no 2-hour slots here. So we'll make do. Double. So then here, when we go to running, we can capture what we were at. Do this. Does that make sense? Did I get all the signs right? Basic idea is we capture the encoder when we 0, and then from there, we can use it. I feel like I'm missing a minus sign. Is that right?
Minus initial position.
Yeah. Oh, our test will be pretty clear on if we got it right. Just pass. Let's see. Yeah, looks a lot better. Okay. Okay, so let's go through a thought exercise. We're starting to get close, right? We're seeing all the behavior we want. It's zeros. We're seeing a good position. So what other tests do we want to run? What things are we worried about? We tested. Well, this is the basic test, right? What else do we test?
Speed.
How would we? What do you mean by that?
How fast it's going.
I think we're having to go full speed, right?
I guess because you're well.
It's flying at full voltage.
If it's boundaries,
That's a good one. So how would we test that?
you can't be above its max position, and you can't be below your.
Okay. So do we try and send it 10 meters? See what happens? I don't want to write the file twice. The rest of this makes sense? Oh, no, I need to name the test something else. Okay, let's try it. What should what do I have here? I have a max height. But actually, this is good. So how should we modify our test to catch this? See if to see if it's working. I'm pretty certain we're going to violate this test. We didn't write any code for it.
Well, so you would say you expect below, or from min height to max height.
Okay. So in here, does that look decent? And then you can see here, I have a concept of a soft and a hard stop. Hard stop is the physical limit, and the soft stop is a little above it, a little above the bottom, a little below the top, because we don't really want to slam into our physical limits and break the thing. And I bet this 1 meter isn't right on this robot. I bet it goes higher, but we don't need to go push the limits here. So, okay. Oh my, yeah, we have a problem. Which is expected because we never wrote anything for this case. So, okay, so let's go. How would we fix this? We're running out of people. You got ideas? So we want to put some logic in our code to go and essentially if the user asks for 10 meters, we want to just give them the max allowable.
Do we currently know the max allowable height for the rail design?
K max height.
Oh, okay. Just, can you just write like sort of a test to see if height ask is greater than K max height, well, it just doesn't work? Or K max height minus a tiny bit?
Oh yeah, the soft height. Yep. You're thinking better than I am. Actually, I'm gonna do this slightly differently. I'm gonna use mins and maxes. But exactly what you're proposing. Okay, so we're gonna take the min of the goal and the max height, and then we can take the max, the min, and that other piece. I think that's equivalent to what you were proposing. We'll see. Tests don't lie. Because, yeah, max soft height is slightly below here. We can just up our limit to 1.5 years. This is a competition season, we'd probably measure it or pull it out of CAD or something better, but going fast and loose here. Okay, so max height is 1.5. Okay, so that one succeeds. And then this one, we got to 1.489, and that's still considered a failure. Is that actually a failure, or did our code do the right thing? Okay, so we should fix the check for the test. So what should this be down here? I vote we just see if it's near the hard stop. That seems correct. Okay, let's test 2. So if we go, what should this be for the min height?
It should be like 0 or the 0 value after 0 plus a tiny bit.
Yep. So I think that's our min soft height. Cool. So we're up to 3 tests, so we're doing pretty good. Anything else? At some point we got to start writing tests and turn it on. So let's brainstorm some other things we might want to try. See if we can think of other failure cases. This is great. We have an environment where we can try anything we can program up, and we don't break anything.
So right now our code basically just tests if it's 0, it zeros it, and basically just prevents us from going too far down or too far up, right? And it's basically everything.
Pretty much all. I'm having trouble coming up with too much more. Well, so here's some fun things. We could test what happens if the encoder breaks. Right? It'd be pretty easy. We could say after some time, we just freeze the encoder. And then maybe if we wanted to try and detect that, we could. I'm not proposing we do that today. But those are the type of things you can start to do now that you have a little simulation. Or, hey, what happens if one of the motors dies? We can go simulate that. We can do all sorts of cool little things. But okay, I think we're saying we're ready. So let's talk through how we want to bring this up. So right before this, and you can test it, it's literally like half an hour before the clock started, we went and found out where all the motors are plugged in. So we should go confirm that our model's making the assumption that positive voltage goes up and that the encoder makes sense. So let's go print that out. So I'll show you the code I wrote before we got here. This is the boilerplate I've been using. So we call our function here. This is very familiar, right? Oh, another one we could test. We could test what happens if you disable it in the middle. It would be useful to know. So here we call our update function. We pass it in the encoder position. Here I'm reading the encoder from the tone. And then we pass in the Hall effect. And then we pass in is the driver position enabled. And then we go and call the victors and the talons, and we go and set the voltage to whatever we passed in. And then here, we tried really hard to try and make sure that positive is up, but we should go confirm that. So, let's start by checking to see if the encoder makes sense. Long time. Do you want to see the driver station trade? Thank you. It's not great in wire. Log in. Okay. So you can see we're printing out the encoder and the Hall effect. So if we did our work right, when I lift this up, is that about a meter? Getting close. I could be convinced a meter's a meter. It's a very important check. Like, we're trying to make sure that our model matches. We got that, and then, oh, Hall effect. So it's 1 because we're down. It's 0 because we're up. Okay, that's good. So here we're validating our model, right? Trying to make sure that what we programmed, or what we thought, how we thought the robot worked in our simulation matches reality. Because if that's not true, we're going to go slam this into a limiter. So, and then for the next one we want to test, here, I'll do it this way. We're just going to try and drive it up at a fixed rate. And just see if it works, okay? Because if we got it right, it should go up. And we're doing this at a low power, so if we run it into the hard stop, it's not a big deal. Ready? Try it. So just enable it for a moment. Good. Okay. Cool. So up top. Make sure we got that right. So we have passed in positive power here, which should be the same as positive voltage from our loop. And then it went up. Okay. It's all good. Oh, and then I'm pretty lazy here, so we're gonna go to 0.5 meter if no button's pressed, 0.3 meters if I think it was A, and 0.7 if B. So before we go do this, let's make sure we have some pretty conservative numbers here. So does this seem decent? 4 centimeters a second for zeroing speed. That's pretty conservative. The heights are same. We're going to limit ourselves to 4 volts when we're zeroing and 6 volts when we're running. So this is a pretty sane initial tuning. So. Okay. I don't want to be part of this. Okay. You can enable, but I'm covering disable. Go for it. Cool. So go ahead and press the button. Okay, you're good. Hold it. Can you get that right? Button 2, release. Okay. I'm not sure we got that one right. do what? Go ahead and disable. Sorry, I was reading the wrong joystick. Go ahead and try it again. Go ahead and try. Hold it. And release. Cool. So we can definitely tune this, right? But yeah, that was pretty cool. So the first time we ever ran the code on a real robot, it worked. That's pretty powerful. Okay, go ahead and disable. So one thing we didn't do, which is gonna be a little bit fun, we're gonna have to coordinate. This one doesn't start non-zero, so we didn't get to see the zeroing logic. But we can do that. So I'm gonna lift this up, and then I want you to enable it. I'm gonna get out immediately. And is your hand on the disable? Great. Go. So now we're going slowly down. There we go. So that worked. Cool. You can disable. Any questions? You guys see the value? That's good.
So in like the workshop tomorrow, would we be like simulating how all of this works?
You know what I said, it's hiding. When I said there's this get acceleration function, we're gonna walk through the math for that. I said magic happens here. I did this the first time I gave this class, and everyone's like, ooh, what's in the box? So now we have a class on what's in the box. Yeah, tomorrow we'll go over what's in there, which is why it's a little nicer when this is in the other order, when the timing works out, because then we can talk about what's in the box and then use it. But assuming you guys are willing to accept that there's a magic box that we'll go into tomorrow, this works. Cool, okay. Unless there's more questions, I'm done. That's all I got.